Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Start. Okay, so it's a pleasure to have with us Andreas Cross from ETH now in Zurich. Andreas is sort of well known in the machine learning community for his work on submodularity, and he has given a set of, like, his tutorial in was it in ICML 2008? That was like is considered as one of the best tutorials on this subject in the machine learning and allied communities. So he was at Caltech after graduating from his PhD, and then moved to ETH Zurich last year. And so he is now a European researcher in some sense, and he's coming to terms with the pros and cons of the European academic system. So he's not going to talk about that, but he's going to talk about his new work on sequential decision making. So on to
Okay, thank you very much, Pushmeet, for the kind introduction. Thank you so much for inviting me. Thank you all for coming. It's a great pleasure to be here. There's just always so much exciting work happening at Microsoft Research. Today I'd like to tell you a bit about work that we've been doing over the last 2 years or so on sequential decision making in experimental design and sustainability via adaptive submodularity. And this is joint work with a number of people that I'll acknowledge as we go along. And in particular, I'd like to just single out Daniel Golovin, who played a key role in all the projects in this work. Okay, so this work is motivated by what I think is one of the central challenges in AI, namely how should we make decisions in complex, highly uncertain, large environments. In particular, in environments that are partially observable, where we have the opportunity to gather some information in order to make effective decisions. And clearly, there's been a lot of very exciting work in this area, but the general purpose methods that have been developed often are very difficult to scale to even medium-sized problems. So what I would like to talk about in this work is a new tool that we've developed that allows to characterize certain types of sequential decision problems where very simple methods perform provably very well and allow to tackle really large problems. And I'd like to introduce this tool in particular in the context of 2 applications involving sequential decision making, namely experimental design, as well as a sequential decision problem in conservation management. So I'll get into those problems as we go along with the talk. Before I get to what adaptive modularity is, I'd just like to briefly bring everyone up to speed about the classical notion of submodular functions that we are all talking about the same topic. And I'd like to do that in the context of an application that I've spent quite a bit of time working on, namely the problem of optimal sensor placement. Okay? So suppose we'd like to put a bunch of sensors in a building in order to monitor the temperature to, for example, figure out if there's a fire or not. If we would like to optimize such a placement, we first need to somehow be able to model how useful it is to have sensors at certain locations. So we need some model of the world. And in general, we use a lot of probabilistic models where we model the phenomena that we try to estimate as random variables. So for example, we may have a random variable ys that models the unknown temperature at location s. Right? And so we have a bunch of those random variables. We can't observe themselves, but we could put some sensors that allow us to obtain noisy observations of what the true temperature is. So for example, if we have a sensor at location S in the environment, then it would provide us a noisy measurement xs of the true temperature ys at that location. Okay? And then these are random variables, so they're dependent statistically, and we model the correlation usually with some kind of stochastic process or probabilistic graphical model that allows to encode certain statistical dependencies about how temperature at different locations, say, is spatially correlated, and certain aspects about the signal-to-noise ratio of the sensors. Now, once we have such a model, we can use it in order to quantify the benefit of obtaining measurements from a set of locations. And one common choice to do that is to essentially look at the expected reduction in uncertainty by obtaining measurements. So we can quantify the utility of obtaining measurements at a set A of locations when we consider placing our sensors as the difference between the uncertainty that we have about the temperature, what we try to estimate before having any observations, minus the uncertainty that's left after we've made our observations. And this is taken with respect to, taking an expectation with respect to the observations that the sensors are likely going to make. Now this gives us an objective function that takes a set of locations and quantifies how useful that is for the purpose of making good predictions. And that allows us to compare different placements. So for example, if we place the sensors maybe as illustrated here, then we would be able to get pretty good prediction accuracy pretty much all over the place, obtain very high utility. But if we place the sensors very close together, then they provide redundant information and we don't reduce the uncertainty as much. Okay, so now this is an objective function that we can actually try to optimize. So for example, we can ask, well, what's the 10 best locations where I should place my sensors? Now, unfortunately, that is an NP-hard problem, so for very large problems, I may not be able to necessarily solve it optimally, but at least I can try to solve it pretty well. So I can try to look at how some heuristics work of solving this problem. And arguably, the most natural heuristic for this problem is a simple greedy algorithm that just starts having no sensors and iteratively adds the sensor at the location where it provides as much information as possible over the sensors that I already have. Right? So I place one sensor at a time until I've placed all k of those. But I never changed my mind. I never move any of the sensors around that I already have placed. Okay? So now this is not necessarily going to give us the optimal solution to this problem, but we can ask at least how well does this algorithm do. And we can do some experiments. But if you take a small enough problem, you can actually find the optimal solution through exhaustive search or some more involved branch and bound strategies. And it turns out oftentimes the greedy algorithm gets us very close to the optimal solution. Okay? So that's not just on this example, it's a whole bunch of different problem instances that we try. And so the question is any theoretical justification of when we would expect the greedy algorithm to work well? And it turns out the key insight to analyzing the performance are two natural properties. So the first property is very intuitive. It's just a monotonicity property. If we have a placement A consisting of two sensors, X1 and X2, and if we add some sensors to it and compare it with placement B, where we have these 5 sensors, right, 3, 4, and 5 got added to the ones we have, then our utility did not decrease, right? So formally, whenever we have a set A of sensors and we consider adding an element to the set of sensors, our utility cannot decrease, right? And so that's just written in equations here. And so it's useful to think about this difference here, how much does the function increase by adding an element, as some kind of like discrete derivative, if you wish. So how much does the function increase? And I use this notation delta S given A because we're going to generalize that notation later on. And so monotonicity just means these marginal gains are always non-negative. Okay? So this is very, very natural. Right? Adding sensors doesn't hurt. But there's a slightly more subtle condition, but it's also very natural. That's a diminishing returns condition. So if you compare those two placements, A and B, in A we have 2 sensors, Y1 and 2. And again, placement B, we have 3 more sensors. We consider adding 1 more sensor to it, right? Maybe the sensor S here. Then if we add it to the first placement, we gain a lot of additional information. But if you place the same sensor to exactly the same location in placement B, we only get a little bit of additional information. So you have decreasing marginal gains, and that can be quantified using the combinatorial notion of submodular functions. So a set function f that takes sets of items, so it sets of locations, for example, maps them to the reals is called submodular. If whenever we take a set A that's contained in some larger set B, and we consider adding an element to either of those sets, then our function increases more if we add S to the small set than if we add it to the large set, right? Which in our notation just means that the marginal gain of adding S to A is greater than or equal to the marginal gain of adding S to B. Right? That's the notion of submodular functions. And it turns out that for mutual information, at least if the sensors provide conditionally independent noise, one can actually prove that information gain is monotonic and submodular, so satisfies those conditions. And why is that useful? Well, it turns out that it's known that a function satisfies those conditions, then the greedy algorithm works well. So this is a seminal result due to Nemhauser et al., who proved that the greedy algorithm is going to give us a near-optimal solution. So its value obtains at least a constant fraction of about 63% of the optimal value. Okay? And moreover, for optimizing mutual information, this is actually the best that you can hope to get unless P equals NP. So in some sense, it's the right kind of algorithm for this problem. Okay, so this is a very, very useful property in many applications, also outside of computer science. We've been using it in a number of applications related to optimal information gathering, placing sensors in buildings, in drinking water distribution network to detect contaminations, and other kinds of problems. But all these problems that we looked at are non-adaptive, if you wish. So you commit to all the observations that you're going to make before you actually obtain any measurements. There's no feedback. These are open-loop decision problems, if you wish. Right? Think about placing sensors. You commit to all the locations where you want to place those sensors before you obtain any measurements. That's what I mean by non-adaptive. Many applications, we actually would like to take observations into account in order to make better decisions. One example is medical diagnosis. Right? Suppose we are a veterinarian, we would like to decide how to treat this sick puppy here. Right? So what we may want to do is take a test, maybe measure the puppy's heart rate. If the puppy still has a heart rate, then we decide what next test we may want to run. Right? Maybe take an X-ray. Depending on how that looks, we decide on the next test that we should run, and so on. Right? So we end up with a set of tests that we perform, but the set depends on the observations that we've made along the way. Okay? So in some sense, depending on what you see, you take a different path down this tree here that results in a different set of tests that we would like to run. Okay? Right? And what we'd like to do is we would like to come up with a strategy, right, a policy for testing in order to decide how to treat the patient while minimizing our cost. Okay? Now here we are no longer interested in just coming up with a single fixed set, but rather a decision tree, a policy. Right? It's a planning problem. It's a sequential decision problem. Okay? And so submodularity is a property of set functions. Right? That functions take sets and tell us how useful those sets are. What I'd like to understand is there some notion of a property like submodularity that allows us to characterize when simple algorithms work well for such sequential decision problems, such sequential planning problems? That's exactly the question that we asked in this line of work, and I'd like to tell you a bit about what we have been developing in this context. Okay, so let's look into this problem a bit more. Right? So as a concrete example, this diagnosis problem here. And let's model it probabilistically. Right? So we have a random variable y that describes the state of the patient. That's what we are interested in. And then we can perform tests, the outcome of which is again modeled probabilistically as random variables x1 through xn. And for now, for simplicity, let's just assume that the outcome of those tests is deterministic. It's just a fixed function of the underlying variable y. Okay? So why is this useful? Well, let's consider the states that y can take. This is the set here, right? So each of those different pictures here is one possible disease that the puppy can have. And now, suppose we run a test, so we make an observation. For example, we observe that the puppy has fever, right? In this case, we can eliminate some of the hypotheses that are inconsistent with that observation. We can cover those hypotheses. Now, again, if we figure out, for example, that the puppy does not cough, we again eliminate some of those hypotheses. Okay, so we go ahead and cover those. But the problem is that if we consider a new test that we haven't yet executed, we don't know yet what we're going to see. Right? It could either come up 0 or could come up 1, right? Or maybe any out of finitely many discrete labels. Right? And if it comes up 0, maybe we would eliminate those two hypotheses. But in turn, if it came up 1, we would eliminate those hypotheses. Okay? And so what we would like to do is come up with the sequential testing strategy to eliminate all but the correct hypotheses using as few trials as possible. Okay? Good. And here clearly, right, so the value of a test depends on everything that we already have seen in the past. And we have to model that somehow. Okay, so let's try to formalize that problem a bit. So we need to formalize this process of making observations, taking them into account in order to make better actions. So here's the problem formulation we look at. So we, again, are interested in trying to select out of a set V of possible items. And these items could correspond to medical tests that we want to perform, experiments that we're going to perform, but also more general actions that we can perform. Now, these items are associated with some observations, which you model as random variables. So we have random variables, x1 through xn. They take values in some set O of outcomes, which we for now assume it's discrete, but nothing else. And then we have some objective function, which both depends on what we've done, so what items we've picked, and what the state of the world is. And the state of the world is fully characterized by the states that all these random variables take, which is unbeknown to us. Okay. So with the setup, we can now look at policies and the value for policy, right? The value for decision tree. So policy is just what you think it is. It's just a decision tree that tells us what we should look at, and depending on what observation we get, which next item to pick, depending on what we see, deciding which next item to pick, and so on. So it's a tree that looks like this one. And depending on what we see, we take a different path down a tree, select a different set of items, and in this notation here, just use this notation pi of xv, to denote the set of items you're going to pick. So these 3 orange nodes in this illustration here, if the world is in state xv. So if the world is in state xv, we're going to get value f of that set, right, and this assignment of those variables. But we don't know the state of the world, so we're going to average, according to this distribution p, over all states of the world. Okay? This allows us to quantify the value of any candidate policy, any decision tree.
So
right?
Okay, pi is a policy, right?
Pi is a policy.
And pi of xv, what does it mean?
Pi of xv just says this is the set of all tests I execute if the world is in this particular state. Okay? Good. So this is the first value of a policy. And now we can try to find what's the optimal policy. Right? That's the problem I'd like to solve. Right? Now we can say what's the optimal policy pi star that maximizes this value subject to some constraint on the cost. Maybe that no matter what policy you consider, I can pick at most k items. It's this problem here. And, well, even just writing down a policy of size k is exponential in k. Right? So this could be potentially very problematic. And it's clearly this setting strictly generalizes this non-adaptive setting because we have these observations, we need to take them into account. So this is clearly a hard problem. Also in general, if you don't make any assumptions, it's extremely hard to approximate. So the question is, are there certain settings where we can use simple algorithms for solving these kind of problems? And again, what kind of simple algorithm could we think about? Well, let's think of greedy algorithms. So here's the natural adaptive greedy algorithm for this problem. So what does it do? Well, it works as follows. So at any time, it already has made a bunch of observations. So it has picked some tests A, and it has observed the associated random variables. That's what it knows about the world. Okay? Now, based on those observations, they can quantify what's the expected gain, the expected marginal benefit of executing one more action, running one more test. Okay, so we can look at the marginal gain using a similar notation as we had before, right? Marginal gain of adding observation S, given that we've seen XA. And it's defined as follows. So we look at how much does our function f increase if I add S to set A and the world is in state xv versus what I got before adding this item. Now this clearly depends on the state of the world, which is unknown. So all I can do is I can take the expectation with respect to the state of the world. But clearly I would like to take into account everything I know, so it is conditional on the observations. Yes?
So in this
Yeah.
example in the previous slide, what does it mean add an observation to the policy?
Yeah. So it means, this greedy algorithm implicitly defines a policy. Right? So a policy essentially takes a history, takes a bunch of observations we already have, and maps it to the next action that we should perform. Maps it to the next item that you want to pick. Okay?
But that means whenever you have an observation, you're doing some action, right? But how do you add a new item to that?
Let me describe what the policy exactly looks like. Okay? So this is the policy, the adaptive greedy policy, that just starts having selected nothing. Then it calculates the marginal gain, this quantity here, with respect to every single item that I could pick, every single test I could run. Okay? Calculate all those. Greedily pick the best one. Right? And then I pick that item and get to observe the associated random variable. Get to make the associated observation. Okay? Now my observation, right, set of observations has increased. I recalculate the value of all these items. Again, greedily pick the best one, and so on. That's how I do it. Okay? It's a natural adaptive version of this greedy algorithm. Very kind of very natural setting. Well, and we can ask, under what circumstances does this algorithm work well? Yes?
I'm trying to think what the function f is really capturing in this.
So I'll try to describe it in a lot more detail. But in the context of this diagnosis problem, you can think of this function f here essentially modeling the mass of the hypotheses that already have been ruled out by the observations that already have made, which depends on everything else. Okay? Good. So that's the greedy policy. Well, so we know that in the classical notion of maximizing set functions, if the function is submodular, then we can just run the greedy algorithm and get a good solution. Now we're in the process of actually planning, right? Selecting a policy. So the question is, under what circumstances does this greedy policy here perform well? Okay? And once again?
So is this different if from assuming that I'm just looking at a process evolving in time, and each time I have to pick a state?
Yeah.
My best action is, so my f, it becomes like a value function.
Yeah, exactly. So you can think of it this way, exactly. So you can model temporal dependence, you can be independent according to the ordering, it doesn't change things. Okay. But that's exactly how you can think of it. Okay? Good. So that's the setting. So the question is, right, is there some condition under which this greedy algorithm works well? And it turns out there is. And it's a natural analog of this notion of submodularity to such sequential decision problems. We call it adaptive submodularity. And we call a problem instance adaptive submodular if the marginal gains satisfy a similar kind of diminishing returns condition. So if we fix any item that we consider picking, any medical test that we may consider picking, and we look at how much value do we get given that I've made observations XA, and compare that with the gain I would get if I've observed XB, then the marginal gain given XA must be greater than or equal to the marginal gain given XB, as long as XA is what's called a subrealization of XB. And that just means that in XB, I've seen everything I've seen in XA and potentially made some additional observations. Okay? That's the condition. So whenever this condition holds, I must have to have this monotonicity condition with respect to the marginal gain. That's adaptive submodularity. And you also need an adaptive monotonicity condition, which just says the marginal gain of any fixed item S given any set of observations can't be negative. These are strict generalizations of the classical notion of monotonicity and submodularity for set functions, but now defined over value functions, defined over policies. Turns out these conditions are enough to lift off a lot of the results that are known for submodular set functions. So here's an example. It's the guarantee about the greedy algorithm. So now if we take a problem instance that satisfies those two conditions, and we look at the value of the greedy policy, then it's competitive. It obtains a constant factor approximation with respect to the optimal policy, right? But in this sequential setting, right? So it competes with the optimal policy, which could be this exponentially complicated large object that I can't even write down. Okay?
So
yes?
Does this mean that the information gain criteria for learning decision trees is somehow...
That's the next part of this talk.
Okay.
Let's get back to this question.
Okay. Could you give us the definition for what it means XB observes more than XA?
Aha. So this means that A is a subset of B. And it means I've observed the random variables indexed by set A, right, in this case. And I've observed identical outcomes of those variables, realizations. And maybe I've observed some additional random variables, right? And the values of those observations can be arbitrary. Okay? Yes?
And how do you find the best policy? Because you're in each step you're taking the greedy one, but that depends on the probabilities of the future. But how do you know that?
So I described the greedy policy, right, which is one candidate policy, one out of a huge number of policies. And this theorem is a statement about the value of that policy.
But how do you calculate explicitly this minimum? Because the value of observation will depend. The future observation will depend on of the realization as well.
So that's why this notion of marginal gain is taken with respect to expectations. Right? I take the expectation about everything I don't know, conditional on everything I know.
But you need to know the distribution of it.
Yeah, so you need to know a distribution, or a joint distribution over those random variables.
Of the future as well.
So a joint distribution over all those random variables, right? Maybe I know a prior distribution over the diseases that the puppy can have. Okay? There are statements you can make even if you don't have a prior. You can talk about that separately. But for now, let's assume you have this distribution. Okay? That's the setting. This is one result, but it turns out there's actually a number of other results that can be lifted from this classical setting to this adaptive setting, sequential decision problems. Okay, and I'd like to show those in the context of two applications. And as the first one, let's talk more about this optimal diagnosis problem and optimal experimental design using this machinery. And so here's, again, just as a reminder, the setup that we're talking about. Right? So we would like to figure out what is the state of the puppy, right? What's the disease? We'd like to figure out the state of variable y. We can take those tests. The outcome of those tests is a deterministic function given y. Right? So whenever I have some observations, I eliminate certain candidate values of this variable y. Okay? Now, in this case, it's very natural to define the value of a set of an observation as the mass of the hypotheses that are ruled out, in which case the marginal gain of performing an additional test, conditional on some observations, is just the expected mass of the hypotheses ruled out if we were to run test T and we already have made observations XA. Okay, so we take the expectation with respect to the outcome of the test, which is conditional on everything that we've seen, right? And you look at what's the expected mass of the inconsistent hypotheses that we're going to get rid of. That's a very natural criterion that we want to optimize. Turns out it's one that's known. It's called generalized binary search. And turns out in this problem it's actually equivalent to maximizing information gain, maximizing mutual information with respect to Y. Okay? Look, so it turns out that this criterion satisfies these two conditions, monotonicity and submodularity. Here's the proof on one slide. For the sake of time, I'm not going to step you through it. The most important takeaway message from the slide is that it fits on one slide. Right? It wouldn't take me 3 minutes to explain it. I want to save those to get to some other results. But this is nice. So now we know it satisfies those conditions. That means that we immediately know that the greedy algorithm works well for this problem. Now, it turns out, unfortunately, for this application, that's not the new result. It's actually known that the greedy algorithm works well for this problem. This problem is known as the optimal decision tree problem in computer science. And there's actually quite a long history of work in this. The fact that the greedy algorithm works well has been rediscovered a number of times. The best result so far is that the greedy algorithm gives you a logarithmic approximation in terms of cost, right? So at most a 4 log 1 over p min approximation is the best known result so far. Turns out with this new analysis, you can actually improve this slightly. So essentially you can prove it's a log 1 over 4 min. You get rid of this factor of 4. But that alone is not so exciting. What I think is much more interesting is you get this result for free from this one slide proof on the previous slide. Okay, so it's a very, very simple consequence of this characterization. Yeah?
So has this been also started in the context of compressed sensing, where you're trying to recreate a signal, and there the problem is not discrete now the problem is continuous?
This is a very different setting. We can talk about that offline. Okay? Good. But in general, compressed sensing is not adaptive and so on. So it's a very different kind of setting. Okay, good. So this is one result. So this is one, right? So you get this for free from this one slide proof. But what's much more exciting than that is even that since we now have this general perspective looking at those problems, we can try to tackle much more complicated settings, right? And in particular, all the results so far were predicated on the assumption that the outcome of the tests is a deterministic function of Y. Okay, so there's no noise. But in practice, there's always noise. These tests are going to have false positives, false negatives, and so on. You have to be able to deal with that. Okay? So let's try to formalize the case where we have noisy observations. Right? We deal with noisy data. And that actually makes the problem a lot harder. And one of the reasons is that if you have noise, then our observations don't rule out hypotheses. They just make them less likely. Okay, now what does this mean? Well, it means that it's not even clear how I should formalize the optimization problem, right? Because even if I've seen everything, I may still have some uncertainty about the state of the puppy. So let's resolve that, and let's take a decision theoretic perspective. So what we're really trying to do is we're trying to gather information in order to make optimal decisions. Okay, let's take a decision theoretic standpoint. Just want to get enough information to make the right decision. So how one would that formalize that? Well, from a decision theoretic perspective, we would essentially say I have this unknown variable y, right? And I have some actions that I can perform. Maybe in the setting, right, I can decide to either treat the patient or not, perform surgery or not, right? And I have a utility function, which maybe says that if I decide to not treat the patient, but the patient is sick, then that could have severe consequences, right? But you can have some more false positives, false negatives, all with different costs, and so on, right? And so if you knew the state of the patient, you knew what is the optimal action, but you don't know what the state of the patient is. So the best you can really do is maximize the expected utility, right? So you can try to figure out what's the optimal action I should take with respect to my uncertainty, right? And also think about this from the perspective of classification, right? I'd like to figure out what is the hypothesis y, what's the label, right, of some classification task. The x1 through xn are the features that I can observe, right? And all I care about is making an optimal classification decision. My utility is just the 0-1 loss. Similar kind of setting. Okay, that's the problem I want to solve. Okay? So we're in this business, right? We put ourselves in a situation where we've observed everything, run every single test, still have some uncertainty, but there's some optimal action that has minimum cost. That's the action I'm interested in. So I would like to come up with a testing strategy that selectively gathers information, at some point decides to stop, and whenever it stops, it's guaranteed to take the optimal action. This gives you a very well-defined optimization problem, and you can compare different policies with each other and see how well they do in terms of cost. Okay, now this is clearly a very important problem, right? That's received a lot of attention. There's lots of different ways of how one could solve this problem, right? So for example, one could just try to use the results that are known to work well for this noise-free case, right? But also there's lots of heuristics that have been developed for this, right? For example, if you ask a statistician, they would tell you to do Bayesian d-optimal design, so maximizing mutual information with respect to y. That's a very natural criterion. If you ask a decision theorist, they may tell you to maximize value of information, which is the expected improvement in your ability to make the optimal decision. These are all standard criteria that are used on a day-to-day basis in many applications. Turns out none of those are adaptive submodular, unfortunately. That alone may not be the problem, right? Because it just means we're not studying the right condition. The problem is this one. The problem is that you can come up with very simple examples of this optimization problem. Essentially, all those criteria can potentially perform arbitrarily badly, right? So they can have cost that's exponentially larger than the optimal policy.
And that holds true for all type of loss functions?
So you construct the problem instance in a certain way, right?
Okay.
And so we can talk about the details later on. It's a fairly, right, of course, it's somewhat synthetic construction, right? So the worst case example. And in practice, often they work pretty well, right? But let's get back to that issue later on, right? So I have some experimental results. Okay, good. So this is one. So, but now, since they can perform arbitrarily badly, let's see if we can maybe come up with a better way that actually is competitive with the optimal solution. And here's our proposal to do that. And the idea is to take the noisy problem and reduce it to the noise-free problem that we know how to handle. Now, how may one wish to do that? Well, let's look at this setting. So these are the 4 diseases in some sense, right, that we'd like to distinguish. Each of them corresponds to a different action I should take, how to treat the patient. And now let's make noise part of the problem. Let's create different manifestations of those noisy diseases, right, that just differ in terms of what observations I would get if I were to run certain tests. Okay, so for example, there are 2 manifestations of this orange disease here, right? In this simple cartoon example, the second test always comes up 0, third test always comes up 1, but sometimes the first test comes up 0, sometimes it comes up 1, right? But both of those are just manifestations in some sense of the same disease, so I'd like to take the same optimal action with respect to both of those. Okay, that is the setting. And now I can ask, well, how should I test in order to figure out which action I should take? Notice that since we now annotated all these hypotheses with the outcome of the tests, we're somehow back to the noise-free case, right? So we know exactly if we run a test x1, which of those manifestations we're going to get rid of, right? Very natural. Okay.
You've exploded the size of the input.
Yeah, so let's get back to those issues later. Okay? So right now this is purely a cartoon picture. Okay? Good. This is setting. So now let's do the following. So what we're going to do is we are going to group those manifestations of those diseases according to how we should treat. Right? So we have those groups of these manifestations here, right, that belong to the same optimal action. Okay? Good. So now what you can do is you would like to distinguish them. So let's think of those here as nodes in a graph, and we have an edge between any of those noisy hypotheses, right, manifestations of those diseases, if and only if they lead to different optimal actions that we should perform. Right? So you have this graph here, and the weight of the edge just corresponds to the product of the probabilities of these individual hypotheses. And now in this situation, if I run a test, so if I run x1, for example, test 1, and I figure out x1 equals 1, I can get rid of all the nodes that are inconsistent with this observation. Now we have these edges that somewhat dangle around, right? So let's get rid of these as well. And notice that you're done, you've identified the optimal action, if and only if all the edges are gone. Right? So that's a sufficient and necessary condition to to have identified what's the optimal action. So it's very natural as an objective function to consider the total mass of the edges that we cut if we make a certain set of observations. So instead of quantifying some of the measure, right, the mass of the hypotheses that we cut away, we somehow quantify the mass of the edges that we cut away. Okay? That's the idea. Turns out this criterion is in fact adaptive submodular. And we know that the greedy algorithm works well for adaptive submodular problems. So in fact, we get the policy that is competitive with the optimal policy. Okay? That's the idea. And I think it's a nice result. It's really some of the first approximation algorithm for solving value for information in a fairly large class of probabilistic models. Okay? Yes?
But in a way, so your cost function is not defined as the mass of the links, right?
It is defined in terms of the mass of the links in this graph.
But then the result is also with respect to that. So how does it compare now?
No. So the result is defined with respect to the optimization problem I had several slides ago, which says I would like to test such that if I stop testing, I know for sure that what optimal action I should take. That's it.
But the optimal is in terms of cost that you define.
Yeah, but the cost is not with respect to those actions. The cost is monetary cost of performing tests. Right? So every medical cost, maybe every medical test maybe has some cost. I'd like to minimize the expected cost. So this is really the quantity I care about.
Okay.
Right? So this is kind of an interesting result, right? So this criterion is some really weird criterion, really pretty crazy, right? Why should I care about this criterion, right? So, but it's designed in a way that it has these nice computational properties, so it's adaptive submodular, and it has the property that if you optimize it, you make progress with respect to the problem that you're actually trying to solve. That's the idea. Okay, good. So this is theory. How does it actually work in practice? So we use this in the context of sequential Bayesian experimental design problems in behavioral economics. And this is joint work with Colin Kammerer, who's a behavioral economist at Caltech, and his graduate student, Dave Ray. And the idea is the following. So one premise of behavioral economics is that people tend to not act rationally in some sense. At least they don't necessarily always maximize expected utility if given choice between actions with uncertain outcomes. Right? If you think about putting a subject into a situation where they can choose between two gambles, and a gamble is just, in some sense, a distribution of payoffs. Right? Maybe gamble A, you would win $10 with 70% chance, lose $10 with 30% chance. In gamble B, you win $10 with 30% chance, win or lose nothing with 70% chance. Right? If you maximize expected utility, you would like to pick gamble A because you get an expected $4 of gain. Right? But oftentimes in experimental settings, you see that, that subjects are risk averse, they would pick gamble B and so on. Right? So because you would never lose anything. Good. And there's various different theories that have been proposed that explain how people really act under uncertainty, including constant relative risk aversion, portfolio optimization, normalized prospect theory, and so on. And these are different, in some sense, descriptive theories that hypothesize how people may behave. But there was never a comprehensive study really trying to compare and contrast which of those theories actually best describe what people do in certain circumstances. And one of the challenges is that all these theories have parameters, and if you're not very careful of how you choose those parameters, oftentimes they would give you very similar predictions. So it's actually a very challenging experimental design problem. And so we can now ask, well, how should we design experiments to best tease apart those theories? That's exactly what we do. So we formulate this as a Bayesian experimental design problem, where we have a variable y that describes, so that indexes the theory that we'd like to identify, and a variable theta that describes, in some sense, the parameters of those theories. They're correlated, right? And then what are the tests? Well, the tests or experiments we can perform is essentially presenting the subjects with a pair of gambles, these distributions of payoffs, and ask them to choose one of those. Right? And then you have to model a likelihood somehow. And usually what one you do is use some kind of logistic likelihood function. So each of those theories, parameterized by y, and parameter settings give a different value in some sense for value difference for the pairs of gambles. And you would say if this value difference is very strong, very large, I'm pretty sure, right, I would like to have a distribution, right, the value of a distribution of x1 that's close to deterministic. But if some of the theories are ambivalent with respect to both choices, maybe I'm also not so very sure about what answer the subject is going to give. Okay, that's modeled in this setting, right? So that's a very natural way of formalizing this as an experimental design setting. And now we can ask, how do different theories perform in this problem, right? And so one issue is we need ground truth, right? So at least something that we can do is we can take this model, simulate from it. So we pick the theory variable, we pick the parameters conditional on the theory, and then using those settings, we essentially simulate responses that subjects may provide, and we can use different criteria for choosing those tests. Choose a number of tests, then we try to get our best guess, the map estimate for this theory, and see how high is the chance that we got it right. Right? How does the accuracy increase in terms of the number of observations we're going to get? And one natural baseline is just picking tests uniformly at random. It's this yellow line here, right? And one would expect that one should be able to do much better than random. It turns out it's also pretty easy to do worse than random. So here's generalized binary search, which is this criterion, which is probably near optimal in the noise-free case. Performs really poorly in the setting.
I'm confused what you're plotting now. So what's the what are the two axes? This is just the number of tests you're actually performing.
Exactly. So x-axis is the number of tests that are being performed, and the y-axis is the percentage of times that the map estimate, so the maximum a posteriori estimate with respect to the model, agrees with the ground truth.
Where ground truth is the behavior of the subject.
So this is purely in simulation, according to the model. So I'll tell you about the lab experiments on the next slide, but this is purely in simulation. See how well you can actually recover the ground truth according to this model. And so generalized binary search is pretty poorly. This is uncertainty sampling, which is a very common active learning strategy. You would just pick the test that you're least sure about, that you're most uncertain about. Performs really badly. So this is the standard active learning method if you, for example, do active learning in support vector machines. But what actually was very surprising is value of information, which in some sense is the right criterion. That would be the optimal criterion if you could do look ahead. But if you greedily optimize it, you perform very poorly. Okay? Now, fortunately, you can also do better than random. So the standards technique in Bayesian experimental design would be maximize mutual information with respect to y. And that does better than random. But still does quite a bit worse than this, this new adaptive submodular design criterion. Okay?
How many theories do you have?
So in this case, I think this is 4 that we want to distinguish. Okay? Good. So that's the setting. So this is in simulations, right? But actually gets a significant improvement over these standard criteria that I used. Okay. So now let me actually talk about the lab experiments. So our collaborators were very excited about this, and they're running studies. So they brought in 57 naive subjects who they ran through this testing procedure. So they asked them these questions selected by this test, chosen out of a set of about 30,000 possible designs, so pairs of gambles that they're considering to somehow select from, and then run them through a sequence of 30 tests, then perform the maximum and posteriori classification, and this is the classification that they got in the end. Okay, and so here each of those bars corresponds to a different theory, right? That's what you would like to distinguish. So this prospect theory, the two left ones are two different versions of that. Mean value skewness, two different versions. Expected, right, maximized expected utility, and constant relative risk aversion. And there's actually some interesting results. So one, first of all, is that, well, maximizing expected value got a fair amount of experimental support, actually, right? But also there's quite a bit of heterogeneity in terms of the types that subjects were classified into. But maybe the most interesting experimental finding was that there's no support at all for constant relative risk aversion, which is one of the actually most commonly used hypotheses that describe how people make decisions and uncertainty.
So, what were the subjects like?
So undergrads at UCLA.
Okay, so they know probability theory quite well.
Some of them. So yeah.
So the general population, you would
maybe less support for expected value. That's part of the hypothesis. Exactly. Okay, good. So that's the setting. But there's actually something else you can take away from this. So when we first tried to do this, it took us about 40 seconds just to choose the next test. So why is that? Well, you have to actually search through this large space of possible designs, right? What's the next action I want to run? And for all of those, I have to try what happens if I get to see pick gamble A versus gamble B. How would it affect my posterior? I have to score it, and so on. It's very expensive. Okay, so this cost here is independent of the design criterion, right? So visual information takes this long, value of information takes this long, and so on. But it turns out that this criterion that we're optimizing, since it's submodular, we can use some standard techniques that are known for classical submodular functions, so-called lazy evaluations, an accelerated version of the greedy algorithm, which allows us to drastically improve the performance of this algorithm. So I essentially pick the next test in a couple of seconds instead of a minute. And this can really make a difference in terms of running this in an actual lab environment. Okay, so this is one study. They're actually running another study at this moment. But so they're very interested in this kind of machinery. Now let me move on to a different application. So now for something completely different, and it's a sequential decision problem as well, but in a very different area. And it's a collaboration that we've been working on over the last 2 years or so with ecologists at the United States Geological Survey, in particular Sarah Converse and Beth Gardner, and Steve Morey, who's from the US Fish and Wildlife Services. And it's about a resource allocation problem. How should the government invest scarce resources in order to conserve, right, recommend which land should be bought in order to ensure survival of rare and endangered species. Okay? It's not a theoretical problem, it's actually a very concrete case study. Here's the species that they're looking at, as the Musselman pocket gopher, the streaked-horned lark, and the Taylor checkered spot. It's a case study in Washington State. And it's actually quite a complex problem. So first of all, it's quite large. So they go to select out of several thousands of parcels that have quite some heterogeneity in terms of soil types, vegetation, slope, conservation cost. That, of course, clearly affects the model. There's all sorts of important geographical aspects. So for example, if you're a pocket gopher, then an 8-lane highway may be a pretty unsurmountable obstacle. And there's other important aspects. If you really want to maximize long-term persistence, you have to look at species population dynamics. So for example, you have to model reproduction, colonization, predation, disease, famine, harsh weather, and so on. Right? And all of those, of course, are important considerations, modeling the struggle of the survival of those species. Okay, so what we do in order to model those dynamics, we use a common model in ecology called the patch dynamics model. So essentially, what we would like to do is we would like to say if the animals live at certain parcels of land at a certain point of time, right? Where are they going to live the next time step, right? And in the patch dynamics model, you would only model whether a particular subpopulation is present in one of those patches of land or not. Okay, and so we model this, well, the dynamics as a dynamic Bayesian network. There's a lot of parameters associated with those, right? So there we have random variables that describe whether a population is present at a particular location. Clearly, it's unobserved, right? So it's modeled probabilistically. Then there are environmental conditions, and those model all sorts of unknown parameters, right? Survival probability depending on soil type, but also spatially correlated events. So, for example, presence of harsh winters, industrial accidents, and so on, that affects the survival in a spatially correlated fashion. And clearly, there's also what we can control, right? So what can we control is which patches of land that we actually want to recommend for conservation, right? And of course, all of those affect the distribution of where the species are going to be at the next time step. Okay, so that is the setup. Well, where do the parameters come from? So that is where our collaborators really did an amazing work. So they went through the literature, elicited all those parameters from previous studies. For the parameters that were not available before, they essentially held expert panels, got the experts in and asked them to essentially draw curves, right? So how likely do you think that the species is going to remain alive as a function of the patch size that you have? Clearly, there's disagreement, so you have uncertainty in those parameters. You want to model the effect of that uncertainty on your predictions. That's all done in this model. And then that gives you something that you can really reason about. One point I want to clarify, so the map consists of these parcels. These are small atomic units of land that can potentially be bought. And some of those are too small to sustain a subpopulation. So what you do is we look at larger groups of those populations, it's called patches. And what we do is we do not model colonization across those patches of land, but we model all the dynamics within those patches of land. And then the problem becomes choosing those patches of land, in essence, to hedge against the uncertainty about the model parameter and maximize long-term persistence. So that's the objective function, right? We take our model, then we look at which candidate set of patches we may pick, right? And estimate what's the probability of the species still being alive after, say, 50 years of time, according to this model. Right? That gives us an objective function that we can actually try to optimize. Now, inference in this model is hard, so in practice what we do is a sample-based approximation, essentially sample the dynamics from there and essentially try to cover those samples that we get. And that is the objective function that we have. Now we can try to choose those patches in order to maximize persistence. Right? So we can, given some budget that we can spend and given a cost of all these different patches that we can consider, we can ask, well, what's the best investment, right? How can we maximize the persistence subject to this constraint on the cost, which is NP hard, but turns out to be submodular. Okay, so we can use all the machinery that I talked about before. So it turns out here is a setting where you really want to use non-greedy algorithms, but you can still exploit submodularity in order to get good solutions. And here's just one candidate solution that you get for realistic problem parameters that they describe. And so one takeaway message here is that you really get this fairly heterogeneous set of patches, heterogeneous both in terms of soil properties and so on, all the parameters to really hedge against uncertainty, but also spatially heterogeneous to avoid spatially correlated events. But you again want to hedge against those. And also none of those crosses major obstacles, major highways and rivers and so on. Okay, good. So this is the, if you wish, some kind of static version of the problem. So here, just some numeric results. This problem, you can't really solve it exactly. So what we run is essentially these submodular optimization algorithms against some simple baselines just to see how much do you actually gain by optimization. So you compare against random, but you also compare against some simple heuristics. So for example, just greedily maximizing the amount of habitable area for those species. And you can do a lot better by optimization. That's one aspect. But this is really a very simple version of this problem. So when we showed this to our collaborators, they told us that, well, the problem is actually a lot harder than that. So in particular, what you have to do is we only have a certain amount of money every time period. And we somehow have to make optimal use of that, right? But what also does change is both the amount of budget that the decision makers have to invest, but also the actions that they have, right? So the set of patches of land that they can actually purchase changes over time, right? So in some sense, the set of possible parcels VT that's available at every time step changes over time. Okay, and you'd like to come up with a strategy of allocating those resources over time in order to maximize persistence. Another important aspect is that actually as you make decisions, you learn something. So for example, you learn if certain parcels of land are really successful in sustaining the species, and you'd like to take that information into account in order to make your future investments, right? So you really have observations, you'd like to take those into account. Yes?
When you say the set of parcels may change, do you allow the set of parcels to change based on the set of parcels you chose? For example, owners adapt their values
okay, so,
when they see where you're already doing
conservation. So the result I'm going to tell you makes no assumption about how the parcels are going to change. So in principle, they could depend on what you do. But you also didn't take advantage, right? If you somehow were to model the effect of your actions on the availability of future actions, you potentially may be able to do better. Okay? Good. So this is the setting. And, well, it turns out that the objective is adaptive submodular in the setting. It's you can use the machinery that we talked about in this talk, and that's exactly what we do. And translated to this application means that essentially what is recommended is doing some sort of opportunistic allocation. Right? So at every time step, you do the best you can with the budget that you have. Right? So just optimally invest it using whatever non-greedy algorithm you have in order to maximize the persistence. And then whenever we commit to this decision, right, then time passes, budget changes, the set of available parcel changes, and so on. Again, make the best decision you can, and so on, right? And if you look at the value of the final reserve, right, so the total objective that you care about in the end, then it's going to be competitive even against that of the best clairvoyant algorithm, even an algorithm that knows exactly how much budget is going to be available then, right, and which patches are going to be available then. And this is actually a quite general result. This is not just for this particular application, but it holds in general for these adaptive submodular objective functions. Okay, good. So some quantitative results. Here, what can you do? Well, so first of all, one question is how much do you actually gain by being adaptive? Right. So what you could ask is you could come up with a simple solution where you first, in some sense, rank the different choices that you have according to their utility. Right, then somehow figure out how good are they, right, and just pick them as soon as they become available, right, and that's what we mean by a priori optimization. And what this plot here shows essentially as time passes and you pick more and more of those patches according to the recommendations that the algorithm gave you, how does your objective function increase? And it turns out that even if you use very, very simple heuristics for choosing the patches at each time step, just picking them at random, you already do better than this a priori decision, right? By just adapting to this availability, you can actually do a lot better, right? If you do optimize adaptively based on area, you do better than random. But if you actually optimize the objective function that you care about, you do a lot better than those heuristics. Okay, so there's a strong benefit from doing adaptive optimization, and there is actually value optimization, right? So you can actually gain something in comparison to simple heuristics. Yes?
Just think back to the performance claim relative to even adversarial things.
Yeah.
It's how are you ruling out the, you pick the magic patch the first time and I make everything available to you the rest of time. If you don't choose that magic patch, nothing will ever be available to you ever again. So it seems like you shouldn't be able to get more than like zero, you should be able to get anything against.
Yeah, so it's really a competitiveness. So you only compare against that same set of, right? So it's essentially this sequence of when certain parcels become available to you.
Okay, so it's not really adversarial.
No, it's competitive in the no regret sense. You compare against exactly that same set of actions that become available to you. You can talk about it more in more formal details later if you like. Right? But you also don't really try to take advantage that if you make certain actions, then how would that affect you? Right? So that you don't try to compare. Okay? Good. Okay, so this is some numerical tools, but actually if you want to use that, then we actually have to be able to use that in some interactive fashion. So currently we have this decision support tool that we are building that our collaborators can use in order to essentially experiment with the system. This, for example, see if they were to pick certain patches, how would that affect the recommendations for other patches that you should buy, right? If you can exclude certain patches that you should never buy, how would that affect your future choices, and so on, right? And given that the problem is submodular and you can use these highly efficient algorithms, all the recomputation is essentially done in real time. I can show it to you later on the laptop if you're interested. Okay, good. So that's it. So that was a summary of two projects. There's a lot more going on in a general area of submodular optimization, machine learning, and AI, a lot more that can be done. I want to point out, for those of you who don't know about it, I maintain this MATLAB toolbox for submodular optimization that implements a lot of the algorithms for submodular optimization. You can download it from the webpage. And I also want to highlight that we're running this series of NIPS workshops on discrete optimization in machine learning, and the videos are now online on video lectures. Okay, so that's it. I introduced this notion of adaptive submodularity, which I think is a useful set of abstractions of sequential decision problems where simple algorithms work provably well, right? And we know that for problems that satisfy these adaptive submodularity conditions, a lot of the results that are known for the classical setting of optimizing submodular Z functions can be lifted to much more complicated sequential decision problems, and all the results still go through. I told you about some of those, but there's a lot of other properties that adaptive submodular decision problems And I also showed you some implications. There's others that I didn't get to talk about today. There's a really interesting adaptive influence maximization problem. I can talk to you offline. But I think there's also much more to be said about problems that satisfy this property. And I think one interesting takeaway message is, so in general, greedy algorithms are very useful because they're highly efficient, but it's very important to understand when they actually work or not, right? And if you really try to carefully characterize when these algorithms work, then that can lead to new insights about designing new objective functions, which lead to high performance. Okay, that's it. Thank you very much.
Okay, we have time for a very few questions. So, yep.
Yeah, going back to the case where you're looking at the different behavioural economics and trying to figure out which model is more appropriate. Was that graph showing that just choosing new tests randomly performs better than the sort of supposedly intelligent policies that optimize information gain, etc.?
So information gain actually did better than random in this application.
That one, okay.
But a lot of the other ones actually did it quite a bit worse than random. That's actually not a new phenomenon. You actually see this in a number of active learning problems that have a similar flavor. Because if you're not very careful about how you select examples, you can essentially create bias, right? And that can be highly problematic in your ability to generalize.
Okay, so we are running, we are already running late, so let's thank Andreas again, and he'll be available till the evening, so if you want to talk, just contact me. Okay, let's thank him again.